Yep, so this one is about deep reinforcement learning. Believe it or not, the last slide deck, not approximation, the one before this is actually neural networks. I decided to skip that one because frankly, it is a little bit too straightforward for the content in this class, but it was necessary because, hey, if we're going to talk about neural network implementations, you have to provide some understanding of neural networks as well as backpropagation and other stuff. But the content in that slide deck it's laughably straightforward. Here, I'll even scan through it real quick for you. Perceptrons, a little bit about sigmoids, ReLU, softmax, the universal approximation, a little bit about CNNs, inference, how chain rule comes into backprop, and it kind of stops there, I believe. Yeah. Very good slide deck, but unfortunately it's just a little too straightforward for this. I wanted to just get over with the hard shit and then be done. So deep reinforcement learning. Where do we go with DRL here? I think we go here into Q learning. So we talk about DQN. Do we talk about? I think we just talk about DQN only. Yeah. So there's this book for reference. I did not read this, but it looks pretty cool. Might look into it later. There's a lot of famous papers on DQN. This Atari one is probably the most popular one I heard. Even the Stanford course mentioned it a bunch of times, so I think it's worth looking into at this point. So this is how Q functions work as we know it. We take a state in action and we get an action value, but DQN's first landmark feature is that instead of taking state in action, it takes in only a state and then returns a Q value vector. So an example network that may implement this may look like this: a grid world of some kind that has these things on the grid: an agent, goal, pit, and wall. May take in the input as a 4x4x4 tensor and flatten that into an input layer of 64 entries, and then have some hidden layers before outputting a Q vector for values of the actions at that state. So this approach seems great. If we could use a DQN for everything, that'd be awesome. But two dudes decided to say, nope, you can't do that for everything. So here we can prove to you that there is a particular counterexample where if you have a certain configuration of your MDP, then you will end up in a situation where your function approximation will diverge. That's bad, really, really bad. This shows us that approximation methods bring instability to learning. And instability and divergence are bad because if you're diverging, then you are not getting closer to your ideal policy. In fact, you're making things worse. So like in these examples, you see that divergence is pretty high, but these are mostly phenomena called soft divergence. For the most part, soft divergence does show up quite a bit, but after an initial phase, it's gone. However, the deadly triad are present. If you have these three all together at once, you are bound to have divergence and instability while learning. So usually you want to have two, right? Where is it? Yeah, if any two are present, then it can be avoided. But if you have all three, you're kind of screwed. You can't give up this if you're trying to make a scalable solution, so you usually want to trade off one of these two. Catastrophic forgetting happens in situations where moderate changes in the state space become difficult to act on. So like, where's that example? Yeah, like if you have game one right here and then game two, then in game one, you don't really learn much because either action of these two, right or left, will end up terminating the game. So that's not good. So that's the first feature, which is the neural network implementation of the Q function. Now we have the experience replay. So to decouple the chronological correspondence between subsequent steps, you have an experience buffer where you store past steps and then you replay them to train your Q network. So it's kind of like a It's not exactly a synthetic model. Let's not draw that comparison. It's basically a place where you remember your experience. You remember your past moves basically, and you revise it per se. A target net is really handy because you now have a way of performing prediction in a way that doesn't jostle the weights too much. So you get an initial target network and you use that to compute the Q network values for a while. Once the Q network values have been updated, then you copy the Q network values into the target network. So you periodically and what's the word I'm looking for? Every so often modify your target network. So you're not always making changes to your Q network that take immediate effect on your Q values. You're basically allowing them to be frozen for a while and then take effect. So this allows for more stable modifications to the Q values. Autograd. Autograd has there. Yep, I messed up that question. The answer was backward. I chose grad. Backward. Replay buffer. Yeah, these are all implementation of DQN. You can totally look at that online. Yeah, this is how the SAS prime R tuples are broken down into separate vectors. The result of a particular training run for DQN. And then if you want to improve your DQN implementation further, you can have double Q learning. Double Q learning is great for handling the maximization bias issue. And if you want to take it even further, you can also have prioritized replays. So instead of randomly sampling from your replay buffer, you can prioritize which steps to take based on some kind of preference. In this case, it's the TD error. Multi-step control, I don't remember. So we didn't cover n-step targets, but it is covered in the book. The way I understood it is that it's basically, instead of 1 or 2 steps in the environment, it's multiple steps. So like this, in this example, it's n steps. You have 1, 2, 3, 4, 5, all the way to n rewards. And then on top of that, this is double Q bootstrap, so that's pretty nifty. It's not just a normal Q bootstrap. This is double Q, because you can see that here we're using theta for, what is this? Theta for evaluation. Basically, we have theta and theta minus. The theta minus is the older theta set. Which one is being used for what? Argmax. So the new theta here is being used to choose an action, and then theta minus is the old one. It's being used to evaluate. Yeah, that's basically the idea. Yeah, so those are the ones we cover. Oh, we're about to cover these. So A3C is asynchronous advantage under critic. Yeah, I can't speak. Asynchronous advantage actor critic. So these guys are all about having multiple actor learners that act independently, and they explore different parts of the environment. And then they modify some shared parameters. That way you can learn the environment a lot quicker with less computational resources. Yeah, so that's pretty good for that. Yeah, that's A3C. TRPO, the job for TRPO, or like the mantra, is basically to make the biggest step possible. So take the largest step possible to improve performance while satisfying a special constraint. That constraint is KL divergence. So KL divergence is this equation here. Oh, actually, no. This is the equation for KL divergence right here, the second one. The first one here is the surrogate advantage, and the KL divergence equation takes into consideration the surrogate advantage as part of whether or not a certain policy is an acceptable update. Yeah, so the surrogate advantage is broken down into probability of taking a current action, at a state versus probability of taking the current action at a state. Probability of taking an action at the current state according to the current policy and the older one, in proportion to the advantage function. Yeah, that's the advantage function now. Example of computing KL divergence. Yeah, not too bad. PPO is a first order form of TRPO. So TRPO considers how large or how big the difference is in the policy, but PPO just controls the difference of the policy by clipping it. So to clip it, we just make sure that we are within a certain factor of the advantage function whenever we have a high or low advantage value. Yeah, that's fine. So yeah, that's all about DRL. If anything would be the highlight, it'd be PPO and TRPO. A3C2 as well, why not? Because it's mentioned. I really didn't feel that thrilled about learning A3C. But yeah, that's all about DRL. Cool.